So how does the centre of gravity affect stability? When we take a look at the diagram, first of all, remember that all the movements of an aircraft, pitch, roll, yaw, all pivot around the aircraft's centre of gravity. Now, a pitch up moment will increase alpha, which increases the lift. If the centre of gravity is forward of the centre of pressure, then the increase in lift will cause the aircraft to pivot about the centre of gravity and the nose will lower. This is positive stability, and this is desirable. But in level flight, a forward centre of gravity will require a downward force from the tailplane to stop the nose from dropping. This increases drag, increases the stick forces, and can also limit controllability of the aircraft because, remember, as stability increases, control reduces. The stalling speed will also be higher because the downforce from the stabiliser acts as apparent weight, which needs to be balanced by increase in lift. In other words, an increase in alpha. The opposite happens if we move the centre of gravity aft. Now, the additional lift from a momentary nose up attitude here will cause the aircraft to pivot about a point behind the centre of lift, so the nose pitch up will continue, and this is negative stability, and aircraft are designed to avoid this situation. In other words, commercial aircraft are designed to confine the centre of gravity to limits that are forward of the centre of pressure. As the centre of gravity moves aft towards the centre of pressure, stick forces will be lower, as will the stall speed, because there's less downforce required from the stabiliser. If the centre of gravity continues to move further aft, due to, say, a mass and balance irregularity, then we reach the neutral point, where centre of gravity and centre of lift coincide. And this would be like balancing the aircraft on a pole where it could tip either way. It'd be very unstable. So the aft limit should be just forward of the neutral point. It might interest you to know that on an Airbus A320, which is about 38 metres long, the centre of gravity movement during flight or at any time is limited to less than just 2 metres. It doesn't sound much, but also if just 2 passengers from the front of the airplane move to the back, the centre of gravity would change by over 5 centimetres. As we've seen then, the aft limit of the centre of gravity will be just forward of the centre of pressure. The problem is the centre of pressure moves as alpha changes, so we need a fixed point to use as our datum. And this is the aerodynamic centre. It's the point on a wing where the pitching moments are constant regardless of the angle of attack. These pitching moments are the result of lift distribution on the upper surface acting about the centre of gravity. On a straight rectangular wing, this points around about 25% along the chord line from the wing's leading edge to the trailing edge. But on a swept, tapered wing, the point is less easy to determine. First, for a tapered swept wing, we need to establish a mean aerodynamic chord, because not only will the chord reduce towards the tip, as you can see in the diagram here, but the aerodynamic centre moves aft in relation to the fuselage, if you like, because of the sweep of the wing. The mean aerodynamic chord is defined as the chord of an equivalent untwisted rectangular wing with the same pitching moment and lift characteristics as the actual wing. So in simple terms, if we could imagine a plain wing that behaved just like the tapered swept wing, the mean aerodynamic chord would be in the same place. Once we've found our mean aerodynamic chord, the aerodynamic centre will be 25% back from the leading edge, as it is with a normal rectangular wing.